Hello, my name is Laura Castano, and today I'm going to be discussing Lab 2 of Physics 2211, Motion of a Falling Object. The main objective of this lab is to observe the motion of an object, in this case a paper ball, that falls vertically from rest. Utilizing the observational conditions, I will create the observational model using Tracker and two computational models in GlowScript, one in which the only force accounted is the gravitational force, and the other one in which drag force is also taken into account. The main key ideas in this lab is that an object that falls to the ground has a non-constant velocity. The forces acting on the falling object are the gravitational force and the drag force, which is the force opposite to any object in motion. These forces are acting on opposite directions but do not cancel out, meaning that the net force is not equal to zero, which leads to acceleration. This can be described by Newton's second law, which states that an object in motion, its acceleration is equal to its net force divided by its mass, since there is an unbalanced force that causes acceleration in the downward direction. So here we can observe a video of me dropping a paper ball in Tracker to plot its position as a function of time. I set my axis in the origin of a falling object and I tilted a little bit the axis in order to follow the path of the object. Um, I in the y-axis is positive in the upward direction and negative in the downward direction. So now we can watch the video. We can see that the spaces between the red circles become larger as the paper ball gets closer to the ground, due that it is accelerating closer to the earth. Here we can see a downward sloping graph of the position of the y direction as a function of time, and these are its data points. So this is the closed script code of the gravitational model, only considering the gravitational force. The important changes we made in the code is that I added the ball's mass. The initial conditions of the position and velocity are zero because we need to remember that the object starts from rest. The clock starts at 1.2 seconds in my case. This is the gravitational constant. The j hat, which is the unit vector, is positive because it's pointing up in the y component. And in the while loop, I added the time parameter, which I obtained from the data points of Tracker. Because we're only considering the weight force or the gravitational force, the F net is equal to the weight force. And the weight force in this case is the ball's mass times the gravitational constant times the unit vector. And here I also put the Newton's second law in the position of the formula. So as we run this program, we can see that it follows a similar path as the original video, and also the position versus time graph it's also a downward sloping graph. Now we're going to consider also the drag force. So the key differences in this code is that now we have the proportionality constant, which in this case is 0.0085, and it was obtained by for in trial and error until the position was the same as the observed position. And also here, because we're now considering the drag force, which is equal to the proportionality constant times the magnitude of the ball's velocity squared times the unit vector. And because now we have two forces, we added to the F net the drag force. So as we run this program, we can see the two arrows. The first one, the blue arrow, is the drag force, and the gravitational force is the orange arrow. It also follows a similar graph as the other two, which are downward sloping graphs. Here is the graph comparing the observed versus predicted models. First, if we compare the observed model with the predicted model without drag, we can see that as time becomes larger, the models start to deviate. The model predicts the object to fall much farther than what we observe, overestimating its position. This suggests that there is another force from the surroundings interacting with the object. Now comparing the model with the predicted model considering drag force, the model still predicts the ball's position, but much less compared with the other one. The yellow and blue lines are closer together because I fitted the proportionality constant to almost an identical position to the observed motion. For that reason, they are almost the same. Nonetheless, to improve this in the future, I would choose a better proportionality constant to make the final position identical to the observed one. So what does it mean? Which model predicted terminal velocity? First of all, terminal velocity is when the drag force is equal and opposite to the weight. And this somewhat happened in the second model in the yellow line, because as we can see, the line starts to flatten out at the end, becoming linear, suggesting that the object is approaching its terminal velocity. So what if the object was thrown downward? Would that affect the terminal velocity? Actually, the terminal velocity is not dependent on the initial velocity because it happens when the force of the drag is equal to the force of the gravity, so the acceleration is zero. So because the terminal velocity is specific to the object, not specific to the not dependent to the initial velocity, it will remain unaffected and it will not change the terminal velocity at all.